the nature of bonding in actinide systems. Okay, so if you're not familiar with what's going on in radiochemistry, it has experienced a true renaissance over the last 20 years. Said renaissance had been predicted over and over and over again, but it actually is occurring now. There's a number of reasons for this. One is new reactors are coming online that are different from the pressurized and boiling water reactors that we're all familiar with. And for instance, TerraPower has, I think it's finished being licensed and will start being built. They're building the Natrium reactor just up the road from me in Kemmer, Wyoming. And that's not a particularly small, it's more than a 300 megawatt sodium cooled reactor. But there's many small modular reactor designs that you will see deployed. These aren't hypotheticals anymore over the next decade. Nuclear medicine has been one of the largest growth areas. There's been improved isotope production, improved development of chelators, new biological vectors for doing this in a more targeted way, and even some new isotopes brought online. And then, of course, in critical materials, old uranium mines are now reopening. So I just visited one in southwestern Colorado that's near the Utah border, closer to Moab. And this is actually a photo that I took inside the mine, just with a handheld blacklight. You can see the uranyl salts glowing. It was really one of the neatest experiences of my life. But in critical materials, if you work on actinides, you also will be able to develop rare earth recycling and many other separations technologies. So it's a great area to be in right now. That was not true 25 years ago. 25 years ago, it was mostly dead, but it's really been reborn in force. So what makes radiochemistry different, as Steve and I were talking about before this began, is there are a lot of regulatory concerns. You do have to build specialized facilities. But at the end of the day, it's really not that different from a normal synthetic or spectroscopic lab. We are making things, growing crystals of them, and characterizing them. But some of the big differences are, for instance, you might have your radiation safety officer, which is who this is down here in the bottom left, breathing through a respirator. In that case, we were working with berkelium samples. There was, even though they're very carefully contained, you have to be concerned about inhalation risks, and berkelium is a pretty special isotope, and so that's a requirement. You might have, as I have here, a 3,000-pound lead wall that you can roll around and put in front of glove boxes, and that's because in that particular glove box was where our berkelium was. It decays to californium-249, which is a very intense gamma emitter. And one of the rules you have to follow in a radiochemistry lab is called a LARA, which stands for as low as reasonably achievable. And if you were just walking by this glove box, it would be absolutely unacceptable for you to get any kind of dose. And that's the purpose of that wall, is just so for people working around the area that they're not getting an unnecessary exposure. You always work as teams, as I said before. So back when my students would let me work in the lab, this is me mounting, I think it was a berkelium crystal, breathing through a respirator, lead vest, double gloved. Your gloves are taped to your lab coat, and sometimes you're even wearing disposable sleeves. If you do all of that, and actually the part that you don't see is there's very sophisticated air handling systems that filter the air so heavily that if you're in a radiologic lab, it's the cleanest air you'll ever breathe in your life. And so it's actually, they're extremely safe facilities. There's just a lot to build. If you do all that, you can work with really special elements. So this little green droplet that you see in this center at the top, that's 5 milligrams of californium-249 dissolved in 30 microliters of water. And it really is radioluminescing the way it looks in this picture. Below this, that's 4.33 milligrams of berkelium-249, which if this was a more intense picture, you would see a faint green glow inside that Teflon autoclave liner. And I'll talk a little bit about what that is today, but these are exotic elements. And one of the things that we've transitioned to over the last 10 to 12 years is applying pressure to these elements as a method of systematically changing the nature of their chemical bonding. So first, I'll talk about these elements under ambient conditions, and then I'll transition to the behavior of these elements under high pressure. So the first thing is you should know is that actinides in general, when compared to transition metals, are poorly studied, which is a very odd thing to say since there's been intense research efforts involving them for more than 70 years. But a lot of that is not focused on synthetic chemistry or structural chemistry or spectroscopy. But if you go into the Cambridge Crystal Structure Database and you simply look at the distribution of structures with each of these elements, of course, the largest contributors are going to be uranium, which is naturally occurring and has a 4.5 billion year half-life, or thorium, which is also naturally occurring, which has an even longer half-life than uranium. There's much more uranium chemistry, primarily because it's redox active, has multiple oxidation states, and therefore there's much more you can do with it. I'm not saying that thorium is uninteresting. It actually has the highest known coordination numbers and probably should be better developed. But one of the things that happens is when you move beyond uranium in the periodic table to neptunium, element 93, that is a human-made element. So that is made in a nuclear reactor by bombarding uranium with neutrons. Those neutron-enriched isotopes then undergo beta decay, which gives you one more proton. And that's how you march along the actinide series. So all the elements I'll be talking about today were made in nuclear reactors. The heavy actinides are really only made in one nuclear reactor in the world, and that's the high flux isotope reactor at Oak Ridge National Laboratory. And what's really neat is there's been renewed interest in these elements over the last decade or so, and so their production has continued on. Now, what's happened over the last 25 years is the basic ratios within this pie chart have stayed relatively constant, but the number of entries, the number of structures within each part of these wedges has increased substantially. So when I first put this together, there were about, 2,000 uranium structures. Now there's about 10,000 uranium structures. For neptunium and plutonium, there used to be about 50 of each. Now there's like 400 of each. But what has lagged behind are these later actinides, americium, curium, berkelium, and californium. And we don't even have Einsteinium or fermium structures. Fermium is the last element you can make in a nuclear reactor. And the reason they've lagged behind is multifold. One, none of them have long-lived isotopes, although you could argue that curium has 2 long-lived isotopes, but both of them have significant problems like large spontaneous fission branches, which means you have neutrons to deal with, and neutrons are very hard to shield. Most of them have strong gamma emission, which means for the first time, you're worrying about them as an external hazard. With the earlier actinides, including plutonium, they're really only internal hazards. And so the chemistry of these 4 elements, americium through californium, still lags behind. And so even though when we started, I put 0.01%, that's because in the Cambridge database, there was 1 berkelium structure. It turned out it was a false entry, and there were really 0. Since 2015, about 10 have been published, actually 9, soon to be 10. For americium, it's increased, but it's still maybe about 70. For curium, it's less than 20. For californium, it's about 20. And so these are still very understudied elements, and we're trying to determine really fundamental characteristics of their structure and spectroscopy and the nature of their chemical bonding. So one of the real challenges throughout F-block chemistry, and it doesn't matter whether you're talking about lanthanides or actinides, is engaging the frontier orbitals and forming chemical bonds. And this is really one of the things that has changed a lot over the last 20 years. Is it was thought, if you go back decades, that the 4F and 5F orbitals were non-bonding orbitals. And if they're non-bonding, that means that it doesn't matter what the ligand environment is, you can't perturb the nature of the properties of the electrons in those orbitals. And if that was true, from a chemist's perspective, they would be fairly uninteresting. It turns out it's not true. It is true that in the 5F case, it's a low involvement, but it's not 0. And we can gain some control over it. And so the other feature is there are many orbitals that can be involved in bonding. They could be the F orbitals, but you have empty, for the actinides, you have empty 6d, 7s, 7p orbitals that can all act as acceptor orbitals. And then what's even more perplexing is what should be part of the core orbitals, meaning for the 5p orbital that's formally part of the xenon core, and for the 6p orbital that's formally part of the radon core, you wouldn't think about those as bonding orbitals, but they actually have greater radial extension from the nucleus than the 5f orbital, and they will hybridize in some cases with ligand orbitals. So there's this multitude of orbitals that you have to think about when you're understanding the chemical bonding in these systems. Okay, so I want to show you one example of a system that really led us down this rabbit hole where we currently are today. So in this study, what we're doing is we're sequentially going from plutonium-3 to americium-3 to curium-3 to berkelium-3 to californium-3. We're reacting these with boric acid under the same sets of conditions, same scale, sometimes even the same furnace, depends on the particular glove box. And what you can see on the right is actually a real surprise. None of these have the same formula except for the last two. And in the case of those last two, they don't have the same structure. They're polymorphs of each other. The berkelium borate is much lower symmetry. It's actually triclinic with the berkelium center on a general position, whereas the californium compound is monoclinic. It's actually C-centered monoclinic with the californium on a twofold. These other ones are much lower symmetry and don't even have vaguely similar formulas. And more importantly, only this top plutonium compound, which are these dark blue crystals over here, has a lanthanide analog. And this series of reactions really overturned a lot of folklore that especially the late actinides reacted and behaved exactly like lanthanides that had the same ionic radius. Now, the real surprise in all of these actually is in the californium compound. So if we go to the californium compound, I'm not going to go into a lot of the details because I want to talk about the high pressure work, obviously, in the context of this conference. So it's an extended structure. The californium centers are wrapped up by borate chains, and you have an 8-coordinate environment, which is in the form of a distorted square antiprism. All of that is important, and there were a lot of new structural trends we learned from that, but the really big deal is the broadband luminescence. So this exhibits a green glow. It will do that in some compounds by itself, but here we're irradiating it with 420 light. The peak width at half height is 137 nanometers, and the reason that this peak is asymmetric is that we chop the optical cube actually chops off this high energy side. We have collected this data on other instruments where we have the full transition. You notice that there are oscillations in there, as I'll show you later. Those are actually vibronic coupling. This was really an unexpected spectroscopic feature. That green glow had been known for a long time, and it was supposed to be an FDF transition, but if it was an FDF transition, it would be a sharp, narrow transition, not a broadband transition. We measured the magnetic susceptibility on this compound, I think in terms of inverse susceptibility versus temperature. And if you look at this inverse susceptibility versus temperature, this should be a straight line. It's an F9 system. Dysprosium compounds that are also F9 are well behaved. There's a calculated mu effective of 10.65 Bohr magnetons. This actually fits to 6.7. That's a 40% moment reduction. Dysprosium, the reason why we dope a small percentage of dysprosium into our neodymium iron boride magnets, it is as a much higher saturation moment, so it makes them a harder magnet. This should be saturating if it was dysprosium like at about 8 Bohr magnetons, but instead it's saturating at like 2.5 Bohr magnetons. So this is behaving nothing like dysprosium. One of the problems we have with this system, though, is we don't have an isomorphous dysprosium compound to compare it to. So I'll show you another study where we solve that problem. But you have to answer the question, why is it so different from what's expected? And it turns out there are many reasons. I'll only cover a few of those. One of them is that if you look at the nature of the bonding, here we have the 7 5f orbitals. They are acting as acceptor orbitals. So they are forming weakly covalent bonds with the borate oxygen atoms. But if you look at the 7p orbital, which is here and here on the right, that is undergoing significant hybridization with oxygen 2p orbitals. And so I could also show you the 6d, which are acceptor orbitals, and the 7s, which is an acceptor orbital. This was expected to be a highly ionic system for a number of reasons, one of which is there is also an actinide contraction, but instead it's a highly covalent system. And we have to answer why that's true. One of the things we had to do, though, is demonstrate that this occurs in much simpler systems, that borate compound is a complicated three-dimensional structure. So we moved to what I call archetypal molecules, which simply means we're going to take the californium and we're going to bind it with a well-known ligand. As a matter of fact, these sorts of complexes are extremely well known with lanthanides. If you react in excess of this ligand, which is called dipicolinic acid with californium, you can make these tris chelate molecules, and they actually crystallize much better than the borate. So if you look at the physical property of those, you're able to replicate, and as a matter of fact, get much better spectra than occurs in the borate. So here are two crystals of californium tris dipicolinate. We have a spectrometer where we can zero in on a very small area of one of these crystals, or we could do the whole crystal at once. We can change the aperture and collect the photoluminescence spectrum as a function of temperature. And that's actually what you're seeing in this video, is it's getting colder and colder and colder. It's in an oil that freezes at negative 130 degrees Celsius. And you actually want this in a frozen glass. That's the best way to do spectroscopy. And so if you look in the bottom right in the photoluminescence spectrum, you get this broadband transition. As you cool it, the intensity increases because you're decreasing the non-radiative pathways for de-excitation. You get this huge jump by 200% in intensity when it freezes into the glass. So think about the reason you see all those cracks is that's like ice. So it's frozen. Huge jump in intensity, much better resolution of all of these features. We also collected the magnetic susceptibility, and while the moment is not as reduced as you see for californium, it is a reduced moment of 9.3 Bohr magnetons at room temperature. So this is a slew of spectroscopic measurements. I won't go through all of them. The vibrations that you see in the molecule, those oscillations in this photoluminescence spectrum, that is this variation on a breathing mode, which has a frequency of about 600 wave numbers. That's what you're seeing here. The reason it's a broadband transition and not these sharp transitions, because it also has F-to-F transitions, is californium has a metastable +2 state. And we'll see that again in the high pressure studies. The metastability of the +2 state makes ligand to metal charge transfer much easier than it is anywhere else in the actinide series. And so the reduction potential of californium 3 to 2 is about negative 1.5 volts. If you just go one element earlier to berkelium, it's about negative 2.8 volts. And so californium represents a very special place in the actinide series where chemistry fundamentally changes. And that's why you see this broadband photoluminescence. Okay, so now what we're going to do is we're going to investigate similar compounds, but as a function of pressure. So actinides under pressure are very heavily studied and have been very heavily studied since the beginning for very applied reasons. I'll be talking about the fundamental reasons today. And I'm just going to talk about two examples that are in the literature, curium metal and californium metal under pressure. And this work was a large collaborative study. The samples were made by the legendary Richard Hare, who he's passed away now, but he spent his career at Oak Ridge National Lab. He was the first to prepare berkelium and californium in their metallic states, which were truly heroic experiments. When they investigated those metals under pressure, there's a number of interesting things that occur. The first is you start off with a double hexagonal structure. When you pressurize this at about 17 GPa, this undergoes a transition to a higher symmetry face-centered cubic cell. But then what happens is where the really interesting transitions occur. At 37 GPa, this transitions to a very low symmetry monoclinic cell, then to a face-centered orthorhombic cell, and then to a primitive orthorhombic cell. This is much more like the ambient pressure structures of early actinides like uranium and plutonium. And so what you can imagine is happening as you go across the actinide series and the F orbitals contract, those F electrons become highly localized. But as you compress these and allow the bands to hybridize, they start to exhibit the properties of the early actinides. But what's even more interesting with curium, and continues to be of interest, you can see there was a paper published as recently as 2020 on this, is when you try to calculate these structures at various pressures, if you don't include antiferromagnetic coupling in the calculation, you don't get the correct structure. And as a matter of fact, in the case of curium-3, its structure is highly dictated by the magnetic coupling, and that's only known from two other elements, iron and cobalt, although that's occurring under ambient conditions. And so actinides, including the later actinides at high pressures, are really, really fascinating. Now, when you go to californium, it becomes more complicated, just like in the molecules. The first thing is the surface of bulk californium samples isn't trivalent. It's actually divalent. Just like we see the metastability of the divalent state in molecules, this occurs in the metallic state as well. You see the same kind of transitions where you start off with a hexagonal and then a transition to a cubic phase, and then it drops in symmetry just like you saw with curium. But what's interesting is experimentally, you get this large volume collapse from curium-3 to curium-4, the 3 and 4 just denoting the different phases. But these two actually coexist experimentally at the same time, whereas calculations only predict that the californium-3 phase should occur. So there's all kinds of interesting electronic changes that occur even in the later actinides, which you might not have anticipated based upon the contraction of the f orbitals. So now we'll jump right into our work with pressurizing a late actinide system using diamond anvil cells. And I'll tell you, we began the way everybody probably should begin with standard Tozer DACs, the little DACs that you can get from Almax, which operates simply in the turnbuckle design where you twist them, use Ruby standards for your internal pressure gauge. So this is a really neat example. I need to contract that real quick. This is a really neat example because if you could take every actinide molecule and compress it and get an interesting result, I actually think that would be somewhat uninteresting. I would prefer it if you actually had to think about what molecule should exhibit the largest changes as a function of pressure. And so we actually put a lot of thought into designing a molecule that would do that. So this ligand, PIDTC, stands for pyrrolidinone dithiocarbamate. And a dithiocarbamate actually refers, well, let me tell you what a carbamate is. A carbamate has a nitrogen bound to a carboxylate. So a dithiocarbamate simply has the oxygen atoms replaced with sulfur. The pyrrolidinone unit actually solves a crystallographic problem. You can buy the NN diethyl dithiocarbamate, so it lacks this bond, but this exhibits the classic disorder where the ethyl groups have two different positions. And if you have disorder, you lose your high angle data. And if you don't have high angle data, you don't have a high resolution structure. And we need our ESDs to at least be small in the 3rd decimal place and preferably in the 4th decimal place, so we can't have disorder. Okay, now why this ligand? Well, if it's a carboxylate-like unit, that means there's a 1- charge delocalized over this sulfur-carbon-sulfur unit. But it's also delocalized out to the nitrogen. So if you look at the nitrogen-carbon bond, that bond distance is halfway in between the length for a single bond and a double bond. Now, why should you choose that? As a function of pressure, this should be much more polarized than a hard donor system. So if it was a carboxylate, for example, it shouldn't exhibit a large polarizability upon pressurization. Okay, so we'll start off under ambient conditions. You get gorgeous temperature-dependent photoluminescence. So you see these glowing orange crystals. You actually resolve the ligand field splitting, and it's actually quite large. It's about 1,000 wave numbers, which is not the kind of ligand field splitting you'd see with lanthanides. And I'll go to the pressure studies. In black is the room temperature photoluminescence, and you see the resolution of the ligand field splitting. So we'll go to 1 GPa, and you can see that you get a red shift, a small red shift, and a broadening of the transition and a decrease in intensity. You go to 4 GPa, and you can see that it shifts further red and is further broadened. And by the time you reach 11 GPa, even though that looks like it's in the baseline, there's actually several thousand counts in the photoluminescence that are right there. Now, the thing I should remind you of is this is an F to F transition. It's not F to D, it's not hybridized. And so this shifting must involve some perturbation of the 5F orbitals. Okay, so the first thing is we could not do high pressure diffraction on this for two reasons. One is it actually took us a long time to be able to do high pressure single crystal X-ray diffraction well. But the other feature is by about 4 GPa, the crystals crumble. They don't amorphize, but you don't get, it turns into really blurry diffraction peaks. And so this is actually a calculated high pressure structure that was done by Ava. And what you can see is at 0 GPa, this would also be the same as what we determined using crystallography. Your sulfur atoms are essentially co-parallel with each other. But when you pressurize this, one of these turns by about 45 degrees, and then the curium sulfur bond distances contract by as much as 0.137 angstroms. That's a huge contraction. So what effect does that have on the chemical bonding? So here I'm just showing you it pictorially. This is mostly sulfur 3p character, but you can see that it is hybridizing at the curium center with the metal orbitals. So that is causing a dramatic change in the photoluminescence. But what's really surprising is how small of a change of metal orbital involvement is involved, which in causing this gross change in the photoluminescence. So if you use a pie chart to represent a decomposition of the wave function, in other words, what orbitals are mixed together to form that curium sulfur bond, it's mostly sulfur 3p character. There's only a very small curium 5F contribution of less than 1%. There's a much larger 6D contribution, and that's normally what you see with actinides. The quote is that the 6D orbitals do the heavy lifting. That's usually true with actinides. You have a small 7S contribution. But as you pressurize this, what happens is the 5F contribution goes up to about 2.5%, and the 6D goes up by not by nearly as large of a relative change, and then the 7S goes down. What's amazing is that very small increase in 5F orbital contribution is what's responsible for this very large change in the photoluminescence data. So there's a bunch of other questions, though, that we need to answer here. We are about to submit a really beast of a paper. The SI is 83 pages long on a different curium molecule that Ava also assisted with the theory on. And in those systems, what we've learned is the origin of the redshift is you can imagine that as you push your ligands into your metals, you're going to increase electron repulsion, right? And that should destabilize your ground state and your excited states. But you don't know how they're destabilized in a relative sense. And what we've learned in a related molecule is that the ground state is destabilized to a greater extent than the first excited state. And that's what's shrinking the gap and causing the redshift to occur. The broadening out and the loss of the resolution of the ligand field splitting is probably real vibronic coupling. It's one of the three main reasons that D to D transitions are so broad. And so you're starting to see, and I'm being very loose with my language here, but sort of D to D like spectroscopy, except with an F element. And you're accomplishing this by pressurizing the element, by pressurizing the compounds. So let's move on to a system where we expect a much smaller change. So mellitate is the anionic form of mellitic acid. And mellitic acid is a benzene ring with 6 carboxylates around it. And it's very good for forming MOFs. And so mellitate MOF compounds are known throughout the periodic table. So this is the curium version of that. It turns out, so one of the secrets I'll reveal is MOFs actually respond pretty well to pressure. So that's an advantage that if you want to study a more molecular-like system, The local bonding is more like a molecule, but they're fairly spongy, and so they don't crumble apart nearly as easily as your molecular systems, where the intramolecular forces are hydrogen bonds or aromatic stacking, which are much weaker interactions. So if you look at the shifting of the photoluminescence as a function of GPA, in other words, how many wave numbers is the shift per GPA, it's 1/7 of what you see with the dithiocarbamate. And that's because this is a hard donor system. And so that hypothesis is really borne out, is you really do want not just soft donors, but soft, highly delocalized ligand systems. And so what we'll be doing in the rest of this talk is capitalizing on that concept. And so the way you might do that, there's many ways you could do that, but the ligand we chose is a real classic ligand in inorganic chemistry. It's called maleonitrile dithiolate, abbreviated MNT, and it has 2 sulfur donors, just like the dithiocarbamates. It's bound to an ethylene unit and 2 nitrile groups. And what makes this ligand different is twofold. One, it's much bigger delocalization, but 2, this is a redox active ligand, and that's actually what made it famous in the 1960s. There have been some lanthanide studies on MNT-like, although this isn't MNT, but this one is, like complexes with lanthanides. But what you'll generally find in the older literature is sort of, they'll just pick individual lanthanides. You really need to develop the entire series to discern structural trends across lanthanide and actinide series. So we did this with the lanthanides. This turns out this is not a good system for looking at periodic trends. And the reason is really simple. You also have alkali metals in these systems, and you also have a lot of acetonitrile. That's a solvent you're crystallizing these from. You have varying amounts of acetonitrile and varying coordination environments of these acetonitrile bound to the lanthanides. But the good news is even though, there's multiple structure types that don't really correlate with a contraction in the ionic radius of the lanthanides, it contains the same desired molecule, the MNT molecule, which I'll just flip to the americium complex to show you that. This is the molecule on the right. So this is the tetrakiss MNT complex of americium 3. Okay, and that's what we were trying to make in the first place. That's the same molecule that occurs with the lanthanides. You get really, really nice crystals. Actually, we often see gorgeous crystals with americium. It has an ionic radius that's within error of neodymium. This reaction is on a scale where there's less than 5 milligrams of americium, and you still get gorgeous crystals. Almost a textbook photoluminescence spectrum with really good resolution of the different J states in each of the transitions. But let's look at how the metal sulfur bond links correlate with ionic radius. So what you would expect, because of the lanthanide contraction, is that as we go from lanthanum to dysprosium, and we can't make these complexes with cations smaller than dysprosium. There's some important reasons for that, but it's a line with a very good fit. You can see the R squared is about 0.98. If there's covalent bonding with americium and other actinides, you expect those to be below the line, meaning that the metal sulfur bond is shorter than you would expect based on the ionic radius. Reminding you again that neodymium and americium, their ionic radii with modern data is within error of each other. You can see here the error bars. Americium is not on the line. Neptunium is almost in its own universe. Its bonds are really, really short. And that turns out to be a pretty interesting molecule. Okay, so what we've done here is we've made a family of americium complexes. And I really want to put this in context. This is probably one of the only slides that exists where you have a family of americium compounds. Making each one of these is a really big deal. And there's actually 3 different graduate students that have, along with huge teams, that have led different parts of this slide. But what you have here is a host of different donors. The first thing you have is an all aqua donor. The second thing you have is a pure nitrogen donor. The third thing you have is a diglycolamide. This is actually a very ionic system because your donors are ketones or an etheric oxygen atom. And this co-crystallizes with the nitrate anion. And in fact, the transitions are distinguishable from each other, which is pretty cool. This complex contains a mercaptan group, a sulfur donor, as well as an N oxide. So this is a hard soft mixture. And then finally, we go to what we have predicted should exhibit the largest pressure response. And so let's start with the neodymium complex, and we'll begin with the diglycolamide, reminding you that this is a very ionic system. So as you pressurize this all the way up to 7 GPa, if we monitor the F-to-F transitions and how they shift as a function of pressure, they don't shift. I mean, 2 wave numbers is 0, okay? So that is maybe what you would have predicted, but it is really true. But what's really cool is I understand that a lot of labs can't work with trained uranium elements. By the way, we are very open to collaborations. So if you want to come explore your chemistry, but with heavier elements, we're happy to accommodate that. If you look at the neodymium MNT complex, that's actually a fairly respectable shift in the F-to-F transitions as a function of pressure. And so if you design your ligands and choose them well with lanthanides, you can actually get good pressure responses. When we move to americium, let me go through all of these. The DTP complex in green, this is actually the aquo complex, so only water donors. In black is the diglycolamide. In blue is the nitrogen donor system. So that's a moderately soft donor system, but not as soft as sulfur donors. And then we move to that mixed hard soft donor. So this contains sulfur donors as well as the N oxide group. And, you know, the shift is correlating very nicely with, as they get softer, you are seeing larger and larger shifts. In this case, we're monitoring the shift of the hypersensitive transition for americium-3, which is at about 500 nanometers or so. So if you look now at that tetrakiss MNT complex, it is the record holder. So you have a red shift of 71 wave numbers per GPa unit as you pressurize that. And what we also have the californium data. There's actually some neat alterations that occur when you get to californium. These systems are actually, the theory is being finished up. We're actually almost ready to submit the californium, actually to have all of these in there, the paper on the MNT complexes. These are actually really covalent systems, and they do become more covalent as you pressurize them. And so this is really exciting data for us. Okay, where is this going? Well, there's a bunch of places this is going. Obviously, the idea of using a soft donor that is delocalized and also non-innocent, meaning a redox active ligand, there's families of those, and we can put much more thought into which ones will exhibit the greatest polarizability with pressure. Okay, so that's one direction this is going. We're now much better at high pressure single crystal diffraction than we were, say 5 years ago. And so now sometimes the samples amorphize, sometimes the crystals crumble. There's nothing you can do about that. But when that doesn't happen, we're now routinely getting high pressure structures. I think our record right now is about 12 GPa. But what's even neater is I stopped at californium. Einsteinium is available, but in very small quantities. So Oak Ridge makes about 1 microgram every 2 years of Einsteinium 254. You get more of 253, but you don't want that one. The largest batch we ever received was about 400 nanograms. Okay, you can actually do chemistry with 400 nanograms. So it's literally done in a cone vial. The total volume of solvent was 5 microliters. And what's really cool is the heat from the decay of the Einsteinium is such that you use micropipetters to mix the reagents. By the time you get the cone vial over to the microscope, the Einsteinium has boiled the solvent off. And these are crystals. So they're about 1 micron sized crystals of the Einsteinium dithiocarbamate. It's actually a slightly different molecule than I showed you with curium. We could not do diffraction on crystals that small when we made these samples, but upon moving here, I put in a very sophisticated diffractometer with super bright sources in a gigantic area detector. And that has done two things. One is we have a bright silver source, which is so much better for diamond anvil work because of the absorption by the cell. Also, you get much higher resolution because the wavelength is shorter with silver. The average data collection time is about 18 minutes with this new system. Those crystals start to crumble in about 20 minutes. And so we could do spectroscopic studies on that Einsteinium complex, but we couldn't structurally characterize it. Today we can. And then, of course, all of you know that those crystals are plenty big for putting in a diamond anvil cell. And based on the chemical transition that occurs at californium, Einsteinium is expected to exhibit those effects, those charge transfer effects, to an even greater degree. And so that's some of the things that you'll see coming out of the lab in short order. So with that, I would be delighted to answer any questions.
Thank you very much, Thomas, for that really stimulating overview. Really opened up a lot of windows here for not only collaborations, but new chemistry. Okay, well, we are open for questions. Please either raise your hand or you can type your question in the chat. We have a few questions out there. Fatima, please go ahead.
Hello. Thank you so much for this presentation. That was perfect. I just have some questions. So as I understand, you still didn't try any high pressure single crystal diffraction on none of that complex. Am I right?
No, we have now done that.
What was the pressure transmitting medium in that case?
So, okay, so you'll be offended by the first medium. When we were first starting this, it's always safety first, and the pressure medium was Vaseline, which I know is not super hydrostatic but we now use a polysiloxane that is probably good beyond 12 GPa. Now we just got maybe a month ago, we just got our diamonds in to go to about 150 GPa, and there we're going to have to use gas loading. And we're probably going to use neon as our pressure transmitting medium. And so I'm actually, I have a trip that is going to be organized to Livermore because they use neon. Los Alamos uses xenon under those kinds of conditions. So for the really, really high pressure work, we'll have to switch to gas loading. So far, we have only gone to 46 GPa with actinides. And the highest pressure single crystal structure, which does include some of these molecules, is about 12 GPa. They'll eventually crumble.
And do you see any changing in the parameter or unit cell? I mean, the space group, because some of the complex which you show us, the bonding also changed. So is only changing bonding inside the complex or also changing in the total parameter?
Yeah, both. I don't have those slides. So that huge paper that we're about to submit with Ava and Laura Gagliardi's group, that has the kind of data that you're talking about in there. So, we do plot the volume of the unit cell, which is determined with high pressure diffraction as a function of pressure. And you often see those discontinuities. So what we've learned in these actinide compounds is those discontinuities don't always correspond to phase transitions. Like sometimes what you're doing is you're compressing the structure, and that's occurring, in kind of a linear fashion, and then it becomes incompressible. I'm using that term loosely, and then you have a different linear trend, but it's a much smaller change in volume. Sometimes it really is a phase transition, and so that's that. Figuring out which one is which can be really hard. So the answer is yes, it's both, and we see both. The discontinuities can sometimes.
And other question is, this one is really interesting for me. So because in inorganic compound, like some complex or MOFs, they change in very, very low pressure. So normally you can see how even the color, we can see some inorganic compound and complex, they change below 2 gigapascal. What
Right.
about this type of compound? They also change at very low pressure or no?
The color certainly starts changing, and that's primarily because the charge transfer transitions will move deeper into the visible as a function of pressure. And that actually can be a problem because in some systems, it obscures the F to F transitions. And so we've lost the ability to measure those. And so sometimes we have to pick lanthanides that have F to F transitions that are far enough out into the near IR that they're not obscured by the shifting charge transfer transition. I agree with you that color changes can be observed at quite low pressures, but we tend to observe the largest, what I'll call macroscopic changes, like redox events or phase transitions or things like that. Typically, those will start occurring at about 4 GPa is where, if I were to pick a number, I would say a lot of the interesting stuff is between about 4 and 8 GPa.
Yes, okay,
Great.
yeah, thank you so much, thank you.
Absolutely.
Stefano, go ahead, please.
Hi. Thank you so much for the very exciting presentation. I really loved it.
Thanks.
I had a question about the curium ethyl carbamate. It was slide 20 or 21. So if I understood correctly, with pressure, the intensity goes down.
That's correct.
And you said that it's attributed to an FF transition. So since the FF is Laporte forbidden, and so it needs like to combine with a vibrational mode, is it possible that pressure quenches some of these vibration modes that are needed for allowing the FF transition?
That is possible. So F to F transitions, and there's a lot of reasons that they break the Laporte rules. One of which is most actinide compounds don't have an inversion center, and the Laporte rules require an inversion center. So you already have relaxation just because you have a high coordination number that's relatively low symmetry, even if it approximates
Okay.
So that's probably the primary mode of relaxation. But you've raised a really interesting point, which is pressure does suppress some vibration, right? And so if I go back, I didn't show this data, but if I go back to, let's take this one. If you collect the photoluminescence spectrum of californium at high pressure, what's really amazing is, of course, each of those oscillations is not one vibrational mode. There's actually 5 within each of those bumps. They're at very similar energy, and they're very similar kind of vibration, but they're not quite the same. When you pressurize it, you actually turn them into individual little spikes because you're suppressing the vibrational broadening. We haven't published that data yet either, but absolutely. We think the origin of the decrease in intensity here is because of vibronic broadening and vibronic relaxation, non-radiative relaxation. But you could be right. We don't have data to support what you just said, but you certainly could be right that we are removing an important vibrational mode that relaxes the Laporte rules, but we haven't seen that from the calculations yet. It could occur though.
Okay. Thank you so much.
Absolutely.
Yes, Pascal, please go ahead.
Yeah, first of all, hi, thank you for a nice talk and very
Hi, Pascal.
results.
Pascal actually spent some time in my lab. It was unfortunately not quite put together yet. Yeah, it's good to see you again.
Yeah, I hope it's now settled out, but yeah, maybe we can talk later.
Yep, absolutely.
Yeah. Okay, to my question. Can you give a guess, because in the end you mentioned redox active ligands, what would be your guess what pressure might be needed to trigger an oxidation for californium, for example, from +3 to +4?
We are working on that specifically. So that is actually Tyler Hines' project. we don't know that we have data that suggests it's occurring under 12 GPa, but it's not conclusive enough yet. We have seen oxidation of actinides starting at about 6 GPa, but californium is going to be harder. And so we have a purely inorganic system where the inorganic anion, like an oxoanion, is capable of accepting an electron. And so we're trying to pressurize that to get the electron to go from the californium to the oxoanion. And there's evidence that that might be working, but it's not strong enough for me to defend at this stage. But it's probably going to be high. There's an additional problem, which I didn't talk about with californium. With these soft donors, when the ionic radius of the metal gets very small and you start pressurizing them, the sulfur donors will find each other and they'll start repelling each other. And so what you'll see is, you know, if you monitor the unit cell volume, it'll decrease and then it'll flatten off because you can't compress the molecule any further because the sulfurs have gotten too close together. What's interesting is that's an opportunity to design a different molecule where you have a mixture of your soft donors, which are big, and hard donors, which are much smaller, so that you can keep compressing. And so that'll be the next place that goes. But there's a whole new level of complexity with the really small actinides with soft donors, is that the soft donors find each other at high pressures.
All right. Yeah, sounds interesting. Thank you.
Yep.
And looking forward to your visit in Frankfurt.
Yep. Come see us again. Yeah, we're going to come see you too.
Nice.
Okay, we have a couple more questions. Christoph, please go ahead.
Hi, Thomas. Excellent lecture. Thank you very much.
Thank you.
At certain moment of your lecture, you mentioned high resolution of your high pressure X-ray data. I wonder what kind of resolution you are getting, because if this is, say, resolution better than 1 reciprocal angstrom, then maybe one could try to refine experimental electron density. That would be a big challenge.
Yes.
But that would probably require modification of different pieces of software. But if you are getting high resolution data and you can put several tiny crystals into one diamond anvil cell in order to improve completeness of your data, that would be a great project.
Absolutely. And you'll be happy to hear that is a funded project. So, so we literally proposed that to DOE. We can achieve resolution as low as 0.45 angstroms. So
excellent. That's a minimum which is required.
Yeah. And okay, so I actually sent graduate students to a workshop to learn how to do charge density modeling in France. The issue that we're facing, and by the way, we also agree you do need to put multiple crystals in and refine it as a twin, and that's not an issue either. The issue that we're facing for charge density mapping is, and we've done this, we have mapped the charge density in americium sulfur bonds, is you need an R internal on the data of less than 1%. And that's really hard. Like we certainly have gotten quite good R internals, including at high pressure of like 3%. But the charge density community probably won't buy it. So we're really going to have to find really perfect crystals that have sub 1% R internals. We have achieved that every now and then, but we have never, ironically, we've never pressurized those crystals that diffract that perfectly. But that is where we're going. And yeah, that's a dream. As a matter of fact, when I sent in my last DOE heavy elements chemistry renewal, I had a picture of the charge density map of one of these americium sulfur compounds. And we've mapped that density. You can really see the hybridized americium sulfur bonds, but I've shown it to some charge density experts and they don't believe it's quite publishable. So that's the reason you haven't seen in the literature.
Can I contact you later? I mean,
absolutely.
that's a field, in which I'm active for years now, so I could take a look at the data.
Oh, okay, excellent. All right, that'd be great.
And the second option is that you can try to refine, to perform Hirschfeld atom refinement in order to get experimental structures from your experiments, and that's also very effective and allows to account for relativistic effects for and is usually is improving final crystal structures. So that
we were just
that
told
also could be done.
Yeah, Michael Roof just told us about that. You're absolutely right. The relativistic effects this late in the periodic table are massive. And we really need to start doing that. We just became aware of those kinds of refinements. We absolutely need to transition to that. Yeah.
Okay, thank you very much.
Absolutely.
We have a question in the chat. How did you test the contributions of individual orbitals?
So you test is maybe not the, I probably can't answer it as a test. What you can do is you can do an energy decomposition of the wave function of the bonds. And that's what we're doing here that is taking your curium sulfur bond and determining, you have a wave function for your curium sulfur bond and determining the percentage of each orbital that contributes to that bond. That's done computationally. And what we are proposing is that the increase, for instance, in the 5F orbital here is what's causing this really large change in the photoluminescence. Incidentally, this is, we now know, is normal for curium complexes. All the ones we have pressurized redshift and broaden as you pressurize them. So this is not unique to this system. And so, and we have, in a few of them, the theory is really hard. A few of them we have analyzed the wave function. You are seeing small increases in the 5F contribution. Now, how could you test, like experimentally test that? I don't know. Maybe you could do it with a high resolution X-ray absorption experiment. And we are now collaborating with Christina Kvashnina's group. She's joint between Grenoble and Dresden. She's probably one of the only people that could do that kind of resolution. So maybe that's testable. I'm not sure. So that's, I think, the best answer I can give you.
Great. I did have just one general question about your, when you do diffraction, I mean, you have these heavy elements with huge numbers of electrons, and does that somehow swamp out the resolution that you can get from the other parts of the molecules? Is that an issue for you or not?
Yeah, primarily no, but I'll give you some caveats to that. So it is true that the actinide center is responsible for the vast majority of the scattering, right? And that's what you'd expect. And that does create some complications if the rest of the system is very light. So for instance, the borates are a good example. Boron is a terrible scatterer of X-rays. Oxygen is so-so, but not that great. And so it's routine for you to initially think you have a higher symmetry system than you actually have, because the heavy atoms will mimic centering or some higher order structure. But in fact, the light atoms are create a much lower symmetry network. But, all the programs will initially tell you that, you're C-centered or F-centered and orthorhombic, when in fact, you're really primitive triclinic, and it's just because the scattering is being so dominated by the heavy element systems. There are, in fact, modern structures published by very talented structural groups that we have found are not correct. And it is this exact problem. Is, for instance, we all know when you harvest your reflections, you set that minimum threshold for harvesting. If you set that too high, even slightly too high, you'll find the high symmetry cell that's determined by your heavy atoms.
Yeah.
And if you haven't harvested your your really weak reflections, you'll miss that it's really a much lower symmetry cell. And so you'll see these heavily disordered structures with heavy elements that actually aren't disordered. It's just that they enforced symmetry that doesn't exist. And if you reduce the symmetry to what it actually is, they're nicely ordered systems. So yes, there are those kinds of effects, but the good news is, and this is somewhat surprising, X-ray absorption actually decreases across the actinide series. So the worst offenders are thorium and uranium. By the time you get to californium, if you look at like our absorption coefficients, you might have, I don't know, maybe 100, inverse centimeters. So they're not bad. Like the uranium compounds can be like 300 and 400, and these will be like a third of the early actinide system. So in some ways, there are benefits. They don't absorb as well or as badly, and they really scatter. So those californium borate crystals were plates, and the biggest one we found was 13 microns by about 10 microns by nothing. The plate's thickness was not measurable. If you tried to do that on a light atom system or with a transit, like there's no way, but we have 98 electrons from the californium to scatter. And so that ended up giving a R factor of like 2.7%. So sometimes even on these microcrystals, having that really big scatter in there saves the day.
Wow, great. All right. Well, if there are no further questions, then please everyone join me in thanking Professor Albrecht for a really, really stimulating talk. And please keep us updated on your work and come back again.
All right, thank you. All right. Look
Thank
forward to
you.
more of these seminars. Bye-bye.
Bye.